This is the Portable Functional Near-Infrared Spectroscopy Clinic project of Rowan University's Electrical and Computer Engineering Department. The two undergrads on this project are Autumn Brown and myself, Traz Daczkowski. Our advisor is Dr. Linda Head.
Our goal in this clinic was to create a portable version of the already existing functional near-infrared devices used in experimental environments for medical or academic reasons. As of now, there are very limited versions of these devices that operate portably and none commercially. Due to these limitations, the brain is unable to be observed while doing normal everyday activities. This semester, we were able to utilize a past version of a portable functional near-infrared device that was designed by a graduate student from Rowan University in 2015. When first provided with the device, not all of the hardware components were populated onto the design PCBs, and there was no software implemented onto the MCUs, even though there was code previously written for this project. We were able to fully complete 3 of the boards and perform testing on each.
The MATLAB GUI used for testing was also heavily modified. Compatibility was added for up to 500,000 data points, and the user is now able to highlight up to 5 times that they believe something significant occurred during testing. The user is also now able to record notes in a text box on the bottom of the GUI. The exporting of the data was also improved from an unlabeled matrix of the readings to a struct containing the data, the timestamps of when the user had inputted that a significant event occurred, the settings used to take the readings, and the date and the time of the export of the data.
Through 15 weeks, with the completion and modifications done to the boards, we were finally able to implement the testing of a focus game. This focus game seen in this video allows the user to play a simple game while blood flow readings are taken in the area of the brain.
The focus game shown in this video was created by other Rowan University undergraduate students. In this game, asteroids randomly spawn and the user must shoot them down using their stationary gun that they turn using the arrow keys on the keyboard. Every 30 seconds, in order to keep the user focused on the game, a large enemy ship spawns that requires 10 shots to destroy as opposed to the standard 1 that the asteroids require, and the speed at which the asteroids spawn changes.
Depending on the relative amount of blood flow in the head during the course of this game is what determines whether or not you will see increasing or decreasing peaks in the results. With the use of the timestamps at each 30-second interval, this helps visualize what happens when the user is at a level of more focus as opposed to easier points throughout the experiment. This game and device pair can be used for experimentation to determine a person's level of focus while performing simple tasks and potentially help determine if a person could need medical care for issues in their focus levels. With any experiment come standards and constraints. Like many other projects in the field of engineering, this testing involves the use of human subjects. Due to this, testing was very limited to only those involved with the clinic due to availability and ethical reasons. With this being said, the testing durations also had to be monitored. Although it is generally better to have more points of data, we could not create an experiment where the subject would have to stare at a computer screen for an hour. This would be unreasonable. Instead, a mere 8 minutes was used for testing and was then repeated if more data points were deemed necessary. In our design, we can only use 2 designated wavelengths on the LED array, 730 nanometers for oxygenated blood and 850 nanometers for deoxygenated blood. These are constraints that were not determined by us directly, but ones already calculated by past projects and experiments. Due to this, a big factor that would also affect the results is the skin characteristics of the subject. For each subject, a different amount of light emitting for the photodiode was necessary, or sometimes the sensitivity for a particular wavelength had to be increased so that the results were actually recognizable and meaningful.
We have also begun development of the next generation of our portable FNIR design. The 2 major new features that we are adding are that the device will now have a onboard EEPROM memory chip so that it does not need to have a constant Bluetooth connection to the computer. The other feature that we are planning on implementing is the ability to use up to 6 photodiodes per LED array. This will be achieved by having the photodiodes attached to the main board via flex connectors. The length of these connectors could then be changed at will to vary the depth of the readings in the skull and the penetration of the near-infrared light. With these changes, we hope to have a device that is comparable in functionality with current commercial devices, with the added bonus of portability. Thank you for watching.